Hello and welcome to my presentation on the effects of ionizing radiation on mutation rate in animals, a meta-analysis. There are many sources of ionizing radiation in the environment, and this ranges from radionuclide decay in rock formations and rare earth minerals such as monazite, as well as radon gas found naturally in soil and groundwater. We also receive ionizing radiation from the sun and stars, known as cosmic radiation, which generates regions of the world that have naturally higher background radiation than others. We can also receive ionizing radiation from anthropogenic sources due to uranium mining, nuclear testing, nuclear accidents such as those in Fukushima and Chernobyl, as well as nuclear power plants. So, how does ionizing radiation affect DNA? Well, it can either have an indirect or direct effect on DNA molecules, which can cause either single or double stranded breaks. While we do have DNA repair mechanisms, sometimes these mechanisms fail, which can lead to mutations. Which leads me to my research question. I'm interested in asking, how does ionizing radiation affect mutation rate in animals, and why is there variation in mutation rate across animal species? And so to answer this question, I've conducted a systematic review and meta-analysis of published studies, and I'm looking to analyze the sources of variation. So is this variation across studies due to ecological or evolutionary factors, or due to factors in the study design? So this is actually the first study that quantitatively analyzes these sources of variation across studies. To answer this question, I can break down the data in a variety of ways. I can look at the source of radiation, the mutation identification method, the dose of radiation that was received. I can compare taxonomic differences or life history strategies across the different animal species. I can look at phylogenetic relatedness, which would give me some indication on how evolutionary relationships affect an animal's susceptibility to ionizing radiation. And I can also look at some other exploratory factors. My hypotheses include that I believe that nuclear accidents will show higher mutation rate due to a greater dose associated with them. So these are accidents where the largest release of radionuclides has occurred. In terms of the mutation identification method, I think that unstable chromosome aberrations such as dicentric rings and eccentrics, as well as mitochondrial mutations, will also show increased effect sizes due to their known specificity in detecting radiation exposure. In terms of the dose that's been received by the recipient, I expect that a larger dose will result in an increased mutation rate, so I'm expecting to see some sort of dose-dependent response. In terms of differences across the taxon, I am expecting that ground species will exhibit larger mutation rates, and this is due to the fact that they potentially have more limited dispersal and are more sedentary, so are not able to disperse across regions where doses may differ. And lastly, in terms of phylogenetics, I'm expecting that differences between the studies will not be governed by evolutionary relatedness, but instead they will be governed by more ecological factors. For my literature search, I have plugged in these specific keywords into the Web of Science database to generate papers. And I chose papers based on my study eligibility criteria, which includes these studies must have a direct examination of the effect of ionizing radiation on some measure of mutation rate in a natural population of animal species. They must include a statistical test that examines this relationship, and it also has to include some sort of data that I can extract and convert to a measure of effect size. My literature search has generated 150 studies across 19 different animal species and has also generated 540 estimates of effect size. In terms of my calculations and statistics for this project, I have extracted statistical data from these studies and converted them first to Pearson's R using the Campbell Collaboration Effect Size Calculator for meta-analysis. I have then transformed these values into Fisher-Z transformation values, which are typically used for correlational data. And I've conducted all of my data analysis in R using packages exclusively for meta-analysis. In terms of my different animal taxa in this study, I have 19 different species, a lot of different mammals, a few birds, fish, and annelids. And I've also classified studies based on animals, radiation workers, children of these workers, residents, and children of residents. Looking at the different sources of radiation, I'm including nuclear accidents, nuclear plants, nuclear testing, uranium mining, and regions of high background radiation. Looking at different mutation identification methods, I will be looking at large-scale mutations, including chromatid and chromosome aberrations and micronuclei. And I will also be looking at small-scale mutations, including mini and microsatellites, specific gene mutations, and mitochondrial mutations. I have also extracted many different doses from studies, which I have converted to measures of absorbed dose in gray or absorbed dose rate in microgray per hour, which gives me some indication of the amount of energy that recipients have absorbed. And looking at some results here, I have found that largest effect sizes were generated from uranium mining, as well as potentially from nuclear testing. And this goes against my hypothesis, thinking that nuclear accidents would have larger effect sizes. And this could potentially be due to the fact that uranium mining includes both physical and chemical mutagenicity, so non-radioactive particles that could contribute to this increase in effect size. Looking at the different mutation rate variables, we can see that most of these variables generated really similar effect sizes. However, mitochondrial mutations showed much more increased effect sizes, and this is potentially due to the fact that they mutate much faster. And so I had initially thought that unstable chromosome aberrations would generate larger effect sizes. However, they did not, and this is potentially due to the fact that they do not last very long in the bloodstream. In terms of taxonomic differences to radiation, we see a large effect size in aquatic oligokite worms, potentially due to the fact that they have limited dispersal. And we also see a very large variation across rodents, so it gives me some indication that I need to look into them a little bit more. In terms of my project status, I have yet to look at dose a little more closely and complete a meta-regression. I also will need to examine phylogenetic relatedness across animal species and analyze life history traits. Thank you for watching.